Okay, now finally onto the PCA face recognition algorithm, stepwise and as simple as possible. The first steps will be including training the recognizer, whereas the last steps will include recognizing an unknown face. So let's move on to what are the steps. Now, before we start with the steps of the algorithm, the first part will be to create a training set and then to load it. Now, this training set will consist of total M images. M could be 100, for example. We have a training set of 100 images, 100 face images, and each of these face images will be of size n by n. For example, each of these images will be of size 50 by 50. So it will have total 50 into 50, that is 2500 pixels or 2500 dimensions. That is n square dimensions. Now, once we have our training set, the next thing that we do is we train the recognizer, in which the first step will be to convert each of the faces in this training set into a vector form. As we had discussed earlier in the previous slides, that PCA does not work on the images directly, but it actually converts these images into a vector form. So this is a column vector that has been converted, that this image has been converted into. I have depicted it by a purple bar so that you can easily see the difference as we move along in the algorithm. Now, I just said that this will be of dimension n square dimensions, that is, it will have n square rows or n square values, one value per row, because there's only one column. Okay, I hope you know that much very well. So now I have visualized this face vector space, something like this, so that you have a visual idea where it's which space it belongs to. Now, as you can see, these purple bars are I am representing the face vector mathematically as tor I, that is ith face vector. Now, once we have converted all our face images into face vector forms, the next step in training the recognizer will be to normalize these face vectors. Now, what is normalization? Normalization means that we are going to remove any common features, all the common features that these faces share together. They should be removed from each face. Why? So that each face vector or face could be left behind with only its unique features. As you can see, that for normalizing this the face vectors, that is to remove the common features, what we do is first we find out the common features, and that is given by a average face vector. I have depicted by a green bar, and this is a sign representing an average face vector. As you can see, this is, by the way, for example, if this is the average face of this training set over here, then it will contain, it will look something like this. And that means that each of these face has the features, these features that you can see in the average face. The average face, in fact, depicts the average, as it says, the average features of the whole training set. So naturally it will vary according to whatever the images or whatever the faces of the training set will be. So for example, if this is the average face of the training set, current training set, and it will look something like this. It will have a nose and eyes, eyebrows and mouth and face cutting, etc. Now if we subtract this average face from each of our face vectors, normal face the face vectors depicted by tor I, then we will be left with the normalized face vectors, which I have depicted by the blue bars, as you can see, and the mathematical denotation is by phi I. So now that we have normalized face vectors, the next thing we do is that we calculate the eigenvectors, and eigenvectors are calculated from the covariance matrix. Now the covariance matrix, as we have read earlier, that PCA is done by decomposition of the covariance matrix. How that means that we simply calculate the eigenfaces or principal components from the covariance matrix. Now, covariance matrix itself is given by the formula A into A transpose, where A is nothing but just a matrix with each column being each normalized face vector, as you can see. So if this is the face vector 1, normalized phase vector 1. That is, this is phi 1, phi 2, phi 3, phi I, and 2 phi m. Then each of these, if you place each of the bars or each of the normalized phase vectors as columns of this matrix, it will make up A. So that means naturally A is going to be of the dimensions n squared by m, because there will be n square rows, as we saw earlier, and the m is the number of columns. This is rows into columns, so we have total of m normalized phase vectors. So this is clear that A is going to be of n squared by m matrix. If A is of this dimension, what is this covariance matrix? What is this going to be? What dimensions is this going to be? So let's have a look at that. So if we calculate C as this formula, then that means that if A is of this dimension, naturally transpose will be of reverse dimensions. So naturally C is going to be, by the formula, by the linear algebra formulas, matrix formula, we know that C is going to be of n squared by n squared matrix. That is a very huge matrix. I'll just give you an example. For example, if we had this image as a 50 by 50 sized image, naturally n squared would be 2500. And for 2500, that means covariance matrix will be of size 2500 into 2500. And a covariance matrix this big would generate 2500, that is, would generate n square eigenvectors or principal components. We call eigenvectors as eigenfaces or principal components. So a C this big, a covariance this big, will generate this many eigenvectors, all possible eigenvectors, and each will be of size 2500 into 1. That is as big as the image itself. Now remember that we said that we need to find K significant eigenfaces, because the principle of PCA based face recognition was to represent each image in the training set as a linear combination of K selected eigenfaces, where K is going to be less than M. That is, for example, if M we said was 100, there were 100 images in the training set, then the eigenfaces in which eigenfaces that we are going to use to represent this image must be less than or equal to 100. So either the K eigenfaces, the selected eigenfaces from all this lot, is going to be 100 or below 100. So to find 100 eigenvectors from 2500 eigenvectors, that is going to be a huge amount of calculations, because the eigenvectors, not only that the number is huge, but the dimensions, the size of the eigenvector is also very big. So the system may run terribly slow or run out of memory even, for computations are very huge. But we need to find these eigenvectors in any case of the very same dimensionality. Then what is the solution? How do we get around this problem? The solution would be dimensionality reduction. I'm pretty sure you've heard of it or read it whenever you were reading about PCA, trying to understand it, that eigenfaces or eigenvectors are calculated after the dimensionality reduction of the training set. What did it ever mean? How was dimensionality reduction applied? I never really understood it firstly. Then I studied thoroughly, and later I came to know that this is done simply by calculating the eigenvectors from a covariance matrix with reduced dimensionality. That is to say that not from this covariance matrix. No, the covariance matrix that is going to be used after by the dimensionality reduction is actually will be of a different formula. That is simply I'm just going to show it to you now. So to reduce the calculations and the effect of noise in the needed eigenvectors, calculate them from a covariance matrix of reduced dimensionality. So suppose that this is a lower dimensional subspace of our phase vector space, and this C, the new C that we are going to use to calculate eigenvectors, is given by the formula of A transpose into A. You see this? The above, the difference in both of them, this is reversed. Whatever the C was, we just reversed the formula. And what effect did that give? Now the dimensions will be reversed of both of them. Okay, so first, if it was n squared by n squared, now it becomes m by m, and m we know that was 100. So for example, if m was 100, then n squared was 2500. So now do you see the difference in the number of eigenfaces that will be calculated from this covariance matrix of reduced dimensionality and from the covariance matrix in the original dimensionality? Now, if this covariance matrix generates eigenvectors, they will be total m. You can say that the total number of rows in a covariance matrix gives you the total number of eigenvectors. I think that is how it goes. So it will give 100 eigenvectors at most, and each will be only 100 by 1 dimensional, whereas the eigenvectors in the higher dimensionality, the original dimensionality, were 2500 into 1. Now, is it easier to find K eigenvectors in the above, in this space, or in this space? Naturally, it would be easier in this because, one, the number of eigenvectors will be lesser to find the significant ones in. Two, the size of the eigenvectors is also smaller. So this is the apparent difference in calculating the eigenvectors from a covariance matrix, this covariance matrix in this space, or the covariance matrix after the reducing the dimensionality. So as you can see, I've just explained it. Okay, moving on. Now, the next step in training the recognizer would be, we're not done yet. Now, what we need to do is that, okay, so we have found the eigenvectors in the reduced space. Now what we need to really find is select the K best eigenfaces such that K is less than M and can be represented and can represent the whole training set. Now this is a requirement, that the K eigenfaces must be equal to or less than M, and they must be able to represent the whole training set. They must not leave out any important information about the data that we have here. So, and how are these K eigenfaces that are they are selected heuristically, that is by artificial intelligence procedures. Okay, now one thing more, that the eigenfaces must be in the original dimensionality of the phase vector space. So finding out the significant K eigenfaces from this set isn't enough. What we need to do is we need to map it back to the original dimensionality, that is 2500 into 1 dimensionality from 100 into 1. How do we do that? Now, thankfully, thanks to linear algebra techniques, we know that by this formula, that is an eigenvector, I forgot to mention that UI will depict the ith eigenvector in the higher dimensional space, whereas VI, this VI, is depicting the eigenvector in a lower dimensional space. If we multiply the matrix A, as we had seen before, by this formula, A into the VI, that is this eigenvector, will give us the corresponding eigenvector in the higher dimensional space. So it goes something like this. We take this eigenvector, we multiply it by A, and we get, for example, this was the corresponding eigenvector in the higher dimensionality related to this VI. So this is how, so if we know this formula, naturally we can just select the K eigenfaces in the lower dimensionality, find them out, and then regenerate or map them back to the original dimensionality. So this would save us a lot of computations, and this would also reduce the effect of noise. So when we have our K selected eigenfaces, for example, these are the K eigenfaces, and where each of these eigenfaces I represented by orange bars, these are the selected K eigenfaces in the original dimensionality mapped back, and these are the eigenfaces that will be used to represent each image in the training set. So now do you see that dimensionality reduction has helped or not? We not only avoided a lot of huge calculations. We also actually avoided the effect of noise on the training, on the representation of this face. How was that done? How did we actually reduce the noise? Well, if we had calculated from these 2500 eigenvectors, possibly it could have been that naturally it was based on heuristical selection. So it could have been that we might have added some eigenvectors that were not having these significant features, but in fact had some noise. There could be wrong decisions made, so we could have actually, affected our results of face recognition that way. So we avoided that effect of noise as well. So definitely yes, dimensionality reduction has helped us. Now comes the last part of training the recognizer. Once we have our K selected eigenfaces, now the next thing we need to do is that for each image in the training set, each face in the training set, we will represent this image as a linear combination of these eigenfaces, these K eigenfaces, plus the mean image, the average image. Because if you remember, we had subtracted the eigenface, we had subtracted the average face. So we need to add back the average face because we need to add back the features that we had removed before all the calculations. That is why we're adding the average face here. And if you can see it over here, I don't know, as you can see, we have weights assigned over here, W1, W2, W3, 4, and so on till KF, because there are total. So there are K weights associated with the respective K eigenfaces. Now, these weights are actually the proportions of the eigenface. That is, this eigenface makes up this much percentage of this face. This eigenface contributes this percent to making this face. This eigenface contributes this much percent, and so on, so on forth. Now, this is the face. For example, each face in the training set image is going to be represented in terms of these eigenfaces. Now, this is the weight vector. We just said that these are the weights, right? Now, what does this weight vector do? This is a representation. This is in fact the representation that we had been striving for. This is what PCA's result, this is what PCA's principle is doing. That is, it has finally represented each image in the training set in form of the eigenfaces, K eigenfaces. Now these weights, as you could say that they are the weights or the percentages of the eigenface, the eigenvectors. So if we multiply it by an image, we can get how much person of which eigenface comprises this face. So we need to find these eigenvectors, weight vectors for each of the training set, and these now that we have trained our recognizer where we had a training set of M images, and we calculated the eigenfaces, and we selected K most relevant eigenfaces such that K was less than M. And for each image in the training set, we also calculated and stored associated weight vectors. Now, the next most important, equally important part comes to recognize an unknown face. Now, if an input face is to be recognized, then how it happens? Let's say we have this face as the input image, and we say that this is an unknown person, or we need to know if it is. So the first part would be to convert the input image to a face vector, as we had done in training the recognizer. The next part will be to normalize this face vector as we had done so earlier. And in this case, the average face will be used as was used for training the recognizer, as was calculated in training the recognizer. The next part will be naturally to project normalized face vector onto the eigenspace. Now this isn't something new, don't be scared by the words. What it simply means is that to represent the unknown face as a combination of K eigenfaces, as we had done in training the recognizer. So once we do that, we get a weight vector of the input image, something like exactly like what we had found for each of the images in the training set. Now now that we have our weight vector, what we need to do is we need to compare it to those of the weight vector, to those of the train images and faces in the training set. So once we have the weight vector of this unknown face, we are going to compare it with each of the weight vector of the faces in the training set and calculate the distance between them. Now there will be two cases. If the distance is above, we would have set some threshold value beforehand, and this threshold value will be done in training the recognizer. Now if the distance is going to be less than the threshold, that is, it does not qualify as a known face, so naturally the decision will be an unknown face if the distance is less than the threshold value. But if the distance is above a threshold value, then the PCA Eigenfaces is simply going to return you the name of the person found, the label of the person, the name or label that we had saved earlier in the training set, and the face that it matched with. So this is how recognizing an unknown face is happens by using the PCA Eigenfaces method. So I hope that this was an educational tutorial for you, and it cleared some concepts for you that you might have had trouble with before. I tried my best to explain it in a way that will go seamlessly with the implementation that is coming in the next tutorial, and we will be implementing it in C# again using the EMGCV library, and I think this is good enough recognition basics for you to start the implementation. See you in the next tutorial. Do meet me there. And if you like my tutorial, if you think that this was a worthwhile video to watch, please do give me your positive feedbacks, because that is all that is keeping my website going. Thank you so much.